17.8. Nonsinusoidal waveforms. In this session, we will explore the characteristics of nonsinusoidal waveforms and how they relate to the sounds we hear. We will begin by distinguishing between the physical measurement of frequency and the human perception of pitch. Then, we will discuss the concepts of sound quality and timbre, which allow us to tell different musical instruments apart. We will examine the specific waveforms produced by various instruments and introduce Fourier's theorem, which explains how complex periodic functions can be understood as a sum of simpler sine waves. Finally, we will look at harmonic analysis and Fourier synthesis, including a practical example of how a square wave is constructed from individual harmonics. It is important to understand the distinction between frequency and pitch. Frequency is a physical measurement that tells us the number of oscillations or cycles occurring every second. This is a property of the sound wave itself that can be measured with instruments. Pitch, however, is a psychological reaction to that sound. It is the mental response that enables a person to place a sound on a musical scale, ranging from high to low, or from treble to bass. While pitch is closely related to frequency, it is not a physical property of the sound. Instead, frequency acts as the physical stimulus, while pitch is the human response to that stimulus. The terms quality and timbre refer to the human perceptive response associated with different mixtures of harmonics. This is what allows a listener to distinguish between a trumpet and a saxophone, even when they are playing the very same musical note. For example, we often describe the sound of a trumpet as being brassy, whereas a saxophone is perceived as having a reedy quality. This happens because each instrument produces a unique blend of frequencies. Instruments with similar physical mechanisms, such as the clarinet and the oboe, produce similar frequency mixtures. This similarity in their harmonic content is why an untrained ear might find it difficult to tell them apart based on sound quality alone. When we look at the sounds produced by musical instruments, we find that most of them create non-sinusoidal waveforms. Even if two instruments play the same note, each one will have its own characteristic periodic waveform. The slide shows visual representations of the wave patterns for A flute and A clarinet. You can see that while these patterns are complex and different from a simple sine wave, they both repeat at regular intervals. Crucially, the fundamental frequency of the note remains the same, regardless of which higher harmonics are present. It is this fundamental frequency that determines the pitch we hear, while the unique shape of the wave gives the instrument its distinct voice. Fourier's theorem provides the mathematical foundation for understanding these complex sounds. It states that any periodic function, which we can call y of t, with a period represented by t, can be represented as a sum of sinusoidal waves. This summation is known as a Fourier series. In this series, the function equals the sum of various sine and cosine terms. The fundamental frequency, f sub 1, is equal to 1 divided by the period, t. All other frequencies in the series are integer multiples of this fundamental, meaning f sub n equals n times f sub 1. These higher frequencies are called harmonics. The coefficients, a sub n and b sub n in the equation, represent the amplitudes, or the relative strengths, of each individual harmonic present in the overall sound. Harmonic analysis allows us to visualize the specific ingredients that make up a sound. A tuning fork is a simple case. It produces only the first harmonic, resulting in a pure sine wave. In contrast, instruments like the flute and clarinet produce the fundamental frequency along with many higher-order harmonics. By graphing the relative intensity of these harmonics, we can see why instruments sound different. The graphs on this slide show that for A flute, the second harmonic might be very strong, while for A clarinet, different harmonics like the fifth might be more prominent. These variations in the relative intensity of the harmonics are exactly what define the unique sound and character of each musical instrument. Fourier synthesis is the reverse of harmonic analysis. It is the process of adding various harmonics together to build a complex resultant waveform from scratch. This principle is the foundation of modern electronic music synthesizers. By electronically mixing different amplitudes of any number of harmonics, these machines can generate an infinite variety of tones. Instead of relying on the physical vibrations of a string or an air column, a synthesizer calculates the necessary harmonics to create a specific sound quality. This allows musicians to emulate existing instruments or create entirely new sounds that have never been heard in the natural world. To see Fourier synthesis in action, let us look at the construction of a square wave. A square wave is unique because it is composed only of the odd multiples of the fundamental frequency, such as f, 3f, 5fs, and so on. If we start by adding the fundamental frequency f to the harmonic at 3 times that frequency, we get a wave that looks like a rough approximation of a square. If we continue the process and include frequencies all the way up to 9f, the resulting curve fits the square shape much more closely. As we add more and more odd harmonics, the combined wave approaches the flat tops and sharp edges of a perfect square. Ultimately, an infinite series of these odd harmonics would be required to create a perfect square wave. In summary, we have learned that pitch is a psychological response to the physical stimulus of frequency. The quality or timbre of a sound is determined by the specific mixture of harmonics produced by an instrument. Fourier's theorem is the mathematical tool that allows any periodic waveform to be analyzed as a series of sine and cosine terms. Conversely, Fourier synthesis allows us to create complex waveforms by combining different harmonics in specific ways. Together, these concepts explain how the rich and varied sounds of music are constructed from simple individual frequencies. To conclude, consider these review questions to test your understanding. First, why is it technically incorrect to refer to the pitch of a sound as a physical property? Think about the relationship between the stimulus and the mental response. Second, explain why a clarinet and a flute sound different even when playing the same fundamental frequency. Be sure to use the concept of harmonics and relative intensity in your explanation to describe how their waveforms are uniquely formed.